Hi again. Welcome to the fourth tutorial on simulation using Simscale platform. In this video, we are going to do a computational fluid dynamics problem. Here we are going to improve a rudimentary design by using CFD. Okay, and the problem definition is we have to analyze the air intake manifold for a pneumatic device. The flow rate is given as 0.5 meter cube per second. The fluid is air, and the main objective is we want to improve this particular rudimentary design by analyzing the flow separations and the recirculation in the flow volume. We have the basic dimensions like this for the primitive design. You can model this in the Onshape platform. From there you can bring this to the Simscale, where you can convert the model to the flow volume. Okay, so we will go first to the Onshape platform. I have already modeled this component. You can see this is the procedure. I can explain. We'll start with a sketch in the front plane. From there, this initial portion we will loft. Okay, so the dimension is given already. I will loft this rectangle to this rectangle. Then from there we will go for a sweep. Okay, so a sweep will be done for this rectangle, small rectangle, to this portion. After the sweep, what we are going to do is we will just remove a portion from here. Okay, so you can remove a small portion from here. The dimension is also given, and after that we will go for the shell. Okay, the shell thickness is 2 mm. Okay, so by this we can finish the model. Then we can directly go to the Simscale. We can import this model at the Simscale. Okay, so now we will go to the Simscale platform now, where we are going to import that model from the Onshape. The model is successfully imported. You can see in the tree it is populated intake duct revision 1. Okay, so now you can see, if you wish, you can see the model here. It's already here. And for doing the computational fluid dynamics, actually we need the flow volume inside this duct. Okay, so this manifold inside volume we require. Okay, so for that we can directly do, you can just click here. Then you can go to add geometry operation, where you can go to open flow volume extraction. You can go to open inner region. Okay, so the inner region we are going to extract. Click on that, and then we want to give the boundary faces. Okay, so these are the boundary faces we have to give. Click this one boundary face, then we'll move back side. This is the outlet actually. Okay, so this face and this face. Okay, these are the boundary faces, and you can just seed face, you can simply click any of the inside faces. Okay, so then you can start the extraction. Okay, so this is also this extraction processes will be actually doing in the cloud servers. It will be finished, and volume we can see the extracted volume here. So now you can see the inside flow volume is already extracted. We can now go ahead with the simulation. Okay, for the simulation you can click create simulation, and it is incompressible. Create simulation. All right, I'm giving a revision 1.0. okay, so we are using K omega turbulence model here. You don't want to do anything, tick there. Then we'll go to select the material. We are going to select air, apply. This is the flow volume. It is selected, click. Then we have to go to the initial boundary conditions, click there. We are going to give the velocity inlet. The velocity inlet phase will be here. Okay, so the inlet is this, and we are just going to the velocity type as flow rate. Okay, so in the flow rate we are giving volumetric flow. Okay, so volumetric flow we are giving 0.5 meter cube per second. Okay, so that is the volumetric flow we are giving. We can take. Now we want to go to the outlet. So the pressure outlet, you can just select the pressure outlet here, click. These two are the outlets. Okay, so you can put the gauge pressure as 0. The pressure outlet we finished. Now you can go with the walls. Okay, so the walls you can select. I can select this wall, this wall, this wall, this wall, this wall, this one, not that one, this one, and the downside. Okay, then you can rotate it, this, 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 this. Okay, so now all the wall surfaces we selected. So click. So now all our boundary condition is finished. Okay, so system will automatically make a meshing plan and it will start the simulation. You can click on the simulation and you can go ahead with the run. Okay, so it will almost take 45 minutes and it will use almost 1.5 to 2.6 core hours. Okay, so this problem already solved, and the solutions I can show you here. So that already I solved, and I can directly go to the, after solution you can directly go to the simulation. You can click on the run and post processor result you can see. So first you can see the velocity magnitudes. Okay, so we will add a filter. Okay, so first we'll click on the add filter, then we'll first click a cutting plane. Okay, so that cutting plane we will click and you select Y as the cutting plane orientation. Okay, so after that you can see there is a lot of flow separations and recirculation inside the profile. The velocity distribution you can see it is there are a lot of flow separation areas you can see here, and recirculation also. If you need a better view you can click this vector. Okay, then you can go ahead with the velocity vectors. Okay, so if you look at the velocity vectors you can see this area is recirculation. Okay, so this area is highly recirculating and this area is recirculating, and you don't have an exit on this outlet. Okay, so the fluid all exit on the this there is no flow in this area. Okay, so definitely this design is will not suit our requirement. We want to modify the design. Okay, so the modification which we are going to do is we are just making some filleting. Okay, so this sharp direction changes we will change to gradual by using some bends. Okay, so the new design you can see here where we are just making the same dimension, length will all same, we will just filleting at the sketch this area. We are filleting here as with the radius 100 and this radius is 25. Like that, same in the downside also we are filleting 25 here and 100 here. Okay, so rest all we are keeping same, and also we give a filleting, a 3D filleting at this area. Okay, so that modification we are just giving to the primitive design, and you can go ahead with the modeling that. Okay, so for modeling we can again go to the Onshape where you can do the modeling. So this is the model we are done. The same thing, the only the variation is the sharp corners we fillet it. Okay, so after filleting you can go ahead with the sweep. Okay, so I mean the shell commands. Okay, so first you have to sweep it. After sweeping you have to go for the filleting. Okay, so after filleting then you can go ahead with the shell. Okay, so the last you have to do the shell operation. Okay, so this will be saved in the cloud. Now we can again go back to our Simscale where we will import that model here. Okay, so we will first import that model here again. So the geometry is successfully imported from Onshape. So the first thing is we want to extract the flow volume from this. For that, the same procedure we will do. You can go to odd geometry operation where open inner surface area, surface region, and the same way the faces we can select as the faces as this face, this face, this face. Okay, so these are the boundary faces, and then the seed face you can select any inside surface. Okay, so then we'll go ahead with the extraction of the flow volume. All right, so the inner flow volume is extracted. You can see it is already extracted. Now we can go ahead with the create simulation. Okay, so you can go ahead to create simulation in compressible. Then you can make it as row 1.1. Okay, nothing you want to change. We'll select the material as air, apply. Okay, the volume, flow volume. We'll go ahead with the initial condition. Velocity inlet we will select, where we make this as flow rate. You can change to volumetric flow. You can make it as 0.5 meter cube. Then you want to assign the phase. This is the inlet. Okay, so we click there. Then I'll go ahead with the pressure outlet. We have two outlets, this one and this one. Okay, you can keep the gauge pressure 0. So now it is there. Now we will go for the wall definition. Okay, so we select this, 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 this one, this one. So all the walls are selected. Now you can go ahead with the analysis of all the pre-processing steps we finished. We set up the initial conditions and the boundary conditions. We selected the material also. Now you can click the simulation run and you can go ahead with the start. Okay, so we already finished this also, or we will just go to the finished results. From there we can take it. Okay, so that is for the intake duct 1.1. so we will see how is the results. Okay, you can click on the run, you can go ahead with the post processor. You just select a cutting plane. Okay, so you can select the orientation as Y. Then you can see here the result is much improved compared to the last results. You can see still there is a flow separation here. Okay, so the recirculation areas almost removed. I think we will just see the vector. Okay, so you can see the vector. So there is no circulation, recirculation, all the arrows are going. A slight recirculation you can see at this area. Okay, very slight. And here also there is some problem for the flow. So we want to improve again, but it is far better than the last one. So okay, so you can just see by the velocity vectors. Okay, so the velocity distribution is almost gradual. There is no sudden abrupt variations, but there is a flow separation, a big flow separation at this area. Okay, so that we want to modify. So that is our next variation, how we want to avoid that flow separation. Okay, so to avoid that, the better plan is we want to keep fluid enter in this area. Okay, so for that what I am preferring is we will make some gate vanes. We will fix some gate vanes here. Okay, so that this bend actually it is rotating and moving, so we are just making some guide vanes here. Since this cross section is big, okay, so the fluid is not coming to here. Okay, so for that my idea is to put some guide vanes here, and let's see, after making we will again go ahead with the analysis and we will see how it affect the flow. Okay, so if you want to see the particle flow, you can particle trace, you can simply select the surface. Okay, so this is our flow volume, this is the inlet. So I'll just put a group of particles there. Just increasing the spacing. Okay, you can see how the flow is going. Okay, so then click on and animate and select here as a particle trace. So the yellow areas are the velocity increasing areas. So when it moves through this conical section, when the cross section is reducing, velocity will increase. After that you have a constant cross section throughout the area, but still you can see there are some variation in the velocities. Okay, so this is how we can examine the particle trees. Okay, so now we will go ahead with the third modification, that is we are making some modifications, like we are fixing two guide vanes here. Okay, so the guide vane dimensions it is given here. Okay, the thickness is 1 mm and the distance, everything it is given here. And also we modify the exit. Okay, so there is a sharp separation here, that we made it as a smooth separation. Okay, so these are the final modification we are making. and let's see how this will affect the flow. Okay, so we will just go ahead with the design. Okay, in the Onshape you can see we'll just make we just made two guide vanes here. Okay, so you can just select this plane for the sketching, where you can draw two circles. Okay, so see, these are the two guide vanes. Okay, you can draw that in this circle, I mean in this surface, and then you just extrude it, okay, to this surface. Okay, so up to you can extrude up to this face. Okay, so like that you can make the modification. Also this sharp exit, we make a filleting at that area. Okay, so that are the modification we made, and let's see how this will affect the flow. Okay, so the same way we will import this model, and we will first extract the flow volume from the model, then we will set the primary conditions, like we will select the material, or then this is the analysis we done. So we can select air, then the initial condition velocity inlet we can select. Okay, and I can give as flow rate volumetric flow 0.5 meter cube, and you can set the outlet pressure outlets at the exit, then you can select the walls. Okay, so after that you can go ahead with the run. Okay, so after finishing the run, you can simulation, you can just see the post-processed results. Okay, so we will add first a cutting plane. You can see the velocity magnitude, and you can see significantly the flow separation is minimized. Now we can see all this area, the green color is almost distributed everywhere, only at slight very small areas the color is varying. So the velocity is uniformly distributed, since the cross section is not varying, the velocity is uniformly distributed, the losses will be very less. Okay, so there is the flow separation, you can see it is not as big as we see in the rudimentary design, and the modified design. It is quite impressive, the design is quite impressive. Let's see the vector also. You can just see the vector. Okay, so we'll just make some spacing gap, okay, that you can see in a better way. Okay, so this is the velocity vectors. You can see the flow is almost uniform. In the vein area is directing the flow towards this area, which make the fluid, that flow separation is not here, it is almost gradually changing only. So this is all, this is an improved design. These veins, when we put these two veins, it improved the performance, and the losses is reduced. Okay, so and outlet area also, the flow become smooth, and there is no recirculations. Okay, so the arrows, most arrows are going always downward, there is no flow circulation. You can see there is no recirculations. Okay, so the energy losses will be very less in this final modification. Okay, so if you wish to see the particle trace, you can just select the particle trace. You can just switch off the cutting plane. Okay, then you just select the area where you want to see the trace, just fix there. Then I'm just making the width a little bigger. Okay, Alright, and I'll just go for animation. I'll just select particle trace, and now it's going. Okay, so a smooth the streamlining you can see in the particle trace. Okay, so there is no recirculation. Okay, so the fluid is almost smooth. There is no flow recirculations and flow separations. Okay, so this is a superior design compared to the other two. Okay, so by this I'm winding up this session here, and thank you so much for watching this video. And if you have any additional questions, you can simply make a comment on the link below in the video. I'll try to answer all these questions as soon as I can, and see you in the next video. Thank you very much, and bye bye.